Hello everyone. Let's start our seminar in several minutes. So we can wait for someone else to join us. Did you have a lecture this week or not?
Well, I did not present on the lecture,
Okay.
by the way, so it's hard for me to
Okay.
say.
In that case, we will briefly look on the topic what was being presented on the lecture. Today we'll talk about domain adaptation and more specifically about domain adaptation in NLP. So there are a lot of different domain adaptation methods, for example, supervised, unsupervised, with pseudo-labeled data and so on and so on. This method is widely used in different areas of deep learning, machine learning, and so on. But we will talk about some specific unsupervised methods, namely domain adaptive pre-training, DAPT, and task adaptive pre-training, aka TAPT. It's also widely used methods because, we work with pre-trained language models. So for now, where some pre-trained language models, some transformers, state of art and in most NLP tasks. So that's why we want to have some domain adaptation techniques, especially for these models. So this method was first introduced in the paper called Don't Stop Pre-training. And here on this picture, one can see the main idea of domain adaptation overall, and more specifically these methods, so DAPT and TAPT. So in most cases, we have original language model domain. For example, some pre-trained dump of some big dump of Wikipedia text, for example, on which most of state-of-art language models is trained. For example, Roberto trained on this domain. So BERT trained on this domain, and so on and so on. As far as I know, even GPT and GPT-2 also trained on something like that. All these models includes in their dataset some dump of Wikipedia, for example. So the original domain mostly consists of widely used and written speech. For example, if we want to make a sentiment analysis on Twitter data, we definitely have to adapt our model to this domain because, data from the tweets differ significantly from the Wikipedia articles, for example. Even more, if we want to train our model on some biomedical text, we definitely want to somehow adapt this model to this domain, because in biomedical domain, we have some specific terms, some specific sentence structures, and so on and so on. And these terms are not likely to exist in, for example, Wikipedia articles. So in that case, we have some target domain, for example, biomedical domain, and we have our task domain. In case of biomedical domain, it could be, some medical reports about illness, for example, and something like that. Or it could be some more specific data, for example, biomedical articles. So it's a much more narrow task than the overall target domain. For example, target domain is biomedical data, and task is scientific biomedical articles. So it's both scientific and both biomedical domain in this task. We want what our language model could effectively use data from the target domain and even from the target task. So, well, that's the main idea of all method of domain adaptation. It's so we want to adapt our model to our domain. Well, if it significantly differs from our original pre-training domain. So now let's briefly look at the main outcomes of this paper and work what was done at this paper. So the authors propose a simple but effective method for domain adaptation, even two methods, domain adaptive pre-training and task adaptive pre-training. What is simply to pre-train, to continue pre-train our model on domain, on a target domain, and on the target task. So it's quite a simple idea. It's easy to implement in practice, and surprisingly, this approach gives some interesting and quite a good results, as we can see later. So the main idea is very simple. Again, we simply continue pre-training our model on target domain or target task. For example, if we want to continue training Roberta, we simply train this model on target domain with masked language with MLM objective. So it's quite simple. So our authors considered several domains. It's biomed domains, computer science, news, and reviews. And we also have Roberta base as baseline for our experiments. So as one can see, there's quite a big data sets, and the more interesting part about these data sets, but these data sets all unlabeled, so we don't have to provide some good labeled data. It's enough to have some unlabeled text about some, for example, some articles about computer science. And here one can see cross-entropy loss before domain adaptation and after domain adaptation on these data sets. So we can see what for biomed, computer science, and news domains, not news but reviews domains, domain adaptation lead to improvement in terms of cross-entropy loss. So it's good results, and we can hope that this also helps on our downstreaming tasks, for example, on with classification on biomed articles. And on one domain, cross-entropy loss didn't decreased, so it slightly increased. It was a news domain, and here we can see the vocabulary overlap between these domains. So here PT stands for pre-training domain of Roberta, so it's mostly a Wikipedia dump, as far as I know. And the other domains same as the domains in this table. So we can see what when used domains is significantly overlaps with pre-training domain of Roberta. That's why we don't saw any significant increase in terms of cross-entropy loss. But for our domains where we have smaller overlap in vocabulary, we can see increase, well, we can see decrease in the loss. So our model, well, will get better results on downstream tasks on these domains, probably. Well, we want to check it, of course. So, well, our main idea, what before we adopt some domain adaptation techniques, we have to check if our domain is really differs from the original language model domain. For example, it's a simple rule of thumb, so we can look simply at vocabulary overlap as it was made in this paper. And if we didn't saw any significant overlap, well, in that case, likely domain adaptation will help us to improve our model quality. Well, in our cases, for example, in this case, it's well, we couldn't be sure what in that case domain adaptation will help, but we definitely want to try it because, well, it looks like it's not such a big overlap, for example. So it's definitely better to try to adopt domain adaptation even in that case. And finally, we can see results for domain adaptation pre-training on different domains and on different tasks. So for each domain, authors have two tasks. Well, all of these tasks is text classifications, text classifications. So, well, we can see what domain adaptation in all cases, mostly in all cases except when used, significantly improve the quality on a target task. So sometimes the gap is very high, even, well, more than 10% of F1 score, which is great. And on the other hand, where we can see in our column what is not depth, so it's the same domain adaptive pre-training, but in which case we use not the relevant domain as it was done in this case. So, for example, for these results, authors used biomedical domain for domain adaptation, and for these results, authors use some relevant domain for domain adaptation. For example, maybe where used something like news datasets, as expected, if we will use a relevant domain for domain adaptation, we will get decrease in quality. Well, it's also as expected. And finally, we can look at the final results of the paper. So here we see several columns again. This is baseline with Roberta. This is fine-tuning the classifier after domain adaptive pre-training. This is the same after the task adaptive pre-training. And finally, the most the most costly approach in terms of computational efficiency is the domain adaptive pre-training with task adaptive pre-training, and well, it leads to best results overall. Well, so it's time to say a little bit about task adaptive pre-training. So the task adaptive pre-training is almost the same as the domain adaptive pre-training. So we also made some additional training of our language model with, for example, MLM or CLM objective. But for task adaptive pre-training, we didn't have some big domain datasets. So, for example, for domain adaptive pre-training, we have well, quite big domain datasets, about 7.55 billion of tokens. And for task adaptive pre-training, we have only our task. So for example, it means what we have only data set for this task. So for example, we have data sets for heme prot when we want to classify our well proteins, as I remember, and we don't have any additional data. And even in that case, we can adopt some domain adaptation. So we simply use our target datasets as unlabeled dataset for unsupervised training. So we instead of a vast domain dataset, we use a much more smaller task dataset and conduct some training with MLM objective, for example. Well, again, we can do it without labels, so it's also great in most cases. Well, let's move to the coding part and try to adapt all these methods and compare results with results that authors get in their papers. And also let's look at how we can, well, easily use these domain adaptation techniques in our pipelines, what was presented at the previous seminars. So one more time, we install all the necessary libraries. So it's the datasets from Hugging Face. It's the transformers, again, from Hugging Face. And well, we also import some libraries, some classes, and so on and so on. And we fix our seed to, well, to get reproducible experiments results. So let's start with the simple fine-tuning. Well, it's quite simple. It's a thing what we've done several times in the previous seminars. So we simply want to fine-tune our Roberta model on classification task. Now we will look at ACL ARC dataset. So let's look one more time what it contains. Well, we will explore it in web interface instead of our notebook for this time. So as one can see, there is a preview of this dataset. So we have some text. We have some well, additional fields, for example, paper ID, cited paper ID, well, citing paper year, and so on and so on. And well, this is the data set for intent classification. So our target field is intent, and our text field is, well, text. It's some sentences from the paper. So we want to predict one of available classes. So it's quite simple. It's somehow similar to SST2 dataset, what we looked at before. Again. So let's load this dataset, and again, we will use a Roberta-based model as it was done in paper. So again, it's quite simple. Load dataset, rename target column from intent to label, because we want to use trainer from Hugging Face without any significant change. So that's why we rename our target column. So create tokenizer, define tokenizer function, tokenize our data, add a data collator, because we want to train it in pages as usual, and also define some function to compute our metrics. Well, we want to compute F1 score because well, we don't sure what we have some balanced classes in our data. And also we want to compare our results with results from the paper, and the authors also used macro F1 score. Well, one more time, create model and define our arguments for training. So we'll set some small batch size because, well, that's a value what used in paper again, and set all our parameters to same values what also used in paper. Well, again, to compare with our paper results. So, well, we define everything parameters, so we can start training, I suppose. Well, let's look. Well, great. Training started, and we also still have some free GPU RAM, so it's great. Well, let's wait a little and look at our validation loss and F1 scores. So we can see what our results at the first epoch. It's not so good as expected. Well, let's wait a little. So, well, meanwhile, we can look at results for this dataset. It was presented in paper. So with paper, authors get about 63% of F1 score. Well, but with quite a big standard deviation. So, well, it's quite a noisy result. And again, as we can see, with help of domain adaptive pretraining or task adaptive pretraining, results are significantly better. Well, especially in case of domain adaptive pretraining and combined domain adaptive pretraining and task adaptive pretraining. So let's look what we get. So here we have 63%. Well, right? And here we already have 68%. What's also great. So, well, let's wait a little bit longer. Well, okay. While this model is training, we can look at the next part. What's about task adaptive pretraining? Well, for today, we will mostly skip the domain adaptive pretraining part because, well, if we want to continue pretraining our model on domain data, well, it's take quite a long time. So as we can see for computer science domain, where domain data sets is about, well, 8 billions of tokens. So to adapt this model, we will spend an enormous amount of time. So for domain adaptive pretraining, we will simply load already adapted model. And well, this is the one reason why we look only at the adapt. And the second reason is the adapt. Well, it's almost the same as adapt, because in both cases we simply run mask language modeling task on our data set. Well, the main difference between adapt and adapt is the data set. So, well, the training procedure are the same. So, well, our model is trained. Let's look at the results. And, well, we can see what we obtain, well, very good results. So it's greater when, well, it's bigger when, well, when baseline in paper, and it's even bigger when baseline for tapped. Well, it's look like we use some more effective parameters, or maybe, well, we guessed a very good seed for this training. Also happens sometimes. And well, I suppose it's mostly about parameters because we will set not all the parameters the same as in paper. For example, we trained in a half precision to speed up our training, for example. So it's also good effect, but usually it's affected, well, on our side. Let's do some downgrade usually. Well, For now, let's look at the task adaptive pre-training. So, well, the first step is the same. We load our dataset, we load our model, but for now, we will use not the model for a sequence classification, but we will use model for masked language modeling. Well, this is because we want to adapt a Roberto model. For example, if we want to adapt some GPT models, we will use some conditional language modeling, for example. So this is the important part. So one have to choose the proper model for adaptation of, well, model. So in that case, it will be LLM. Again, tokenize our data. Well, we simply want to tokenize our text without some additional tricks or more advanced preprocessing methods. For example, we could join all of our text in our datasets, and after that tokenize it, and after that split it by chunks. For example, when the one chunk is, for example, contains 128 tokens. So if we do with preprocessing, we will likely obtain more better results. Well, we highly likely obtain better results because we don't truncate any useful information during preprocessing step. Well, or for example, we could mask our data not on the token level, but on the word level. So it's also could, well, improve the final model quality. But in this case, we will use the most simple idea. So we simply tokenize our text, truncate it, and use simple masked language modeling task. So with a probability of 0%, 50, we will mask our tokens during the training. So again, set up some training details. Well, for domain adaptation and for task adaptive pre-training, we will use higher learning rate because it's somehow similar to pre-training where a large language model. So we want to vary parameters of our model much bigger when we usually do it in some fine-tuning setting. So that's why we set higher learning rate. And we also have, again, not so big batch size. For example, on paper, authors use about, well, 256 batch size, as I remember. But here we will use smaller batch size because we want to, well, fit this model in our memory. And that's why we, well, restart runtime. Well, again, because we want to fit this model, this model our GPU RAM. So because we start our runtime, we'll run these cells again. And after that, directly move to the task section. Here we want to retrain this model. So again, we set up all of our parameters, and let's look at perplexity before training. So this is the perplexity of our model on the target task without any pre-training. So we can see it's quite, well, it's not quite high. Yeah, well, it's a good value, but we want to make it even better. So we run our task adaptive pre-training. So again, there's nothing unusual. Where overall training loop is the same for all previous tasks. So it's almost the same as, for example, for text classification. Here we can look at our validation loss. Well, I suppose what we wouldn't wait for a whole loop is ended. So we'll wait for several more epochs and start with training. Well, we simply wait while we get some reasonable validation loss and looks at how our perplexity decrease after this training part. So, well, perplexity is a common measure for evaluating language models. So, to put it simple, it's cross entropy loss on validation. It's exponent of cross entropy loss on validation. And one can, check if the model became better after training using this as a metric. Let's wait for 1 or 2 more epochs and move to the next part. So let's look for, we'll get some decrease in validation loss. And let's wait while this model is saved. Yes, it's saved, so we can stop our training part. And let's check perplexity after this training procedure. We can see what the perplexity is decreased almost twice. It's great. So we can suppose what this model will show better results on the downstream task. So again, let's load our model in the text classification pipeline. So for now, we'll load our pre-trained model. So as we can see, we saved this model to this directory. So now we'll load this model again. And again, do the same thing what we done for fine-tuning part, for text classification part. So we set up the same parameters, run the same training loop, made the same optimization, and so on and so on. And the main difference is what we used another model. So now we will use the task adapted model. And let's start our training. Again, let's wait a little and we can return to, let's remove this output. Return to the results on the count fine-tuning task. So we can see what we started from 0.24 F1 score and resulted in about 75% in F1 score. So we can look at what results we will get with task adapted model. So we can see what we started even worse. But again, we can see what at the second step and at the third step, we obtain much better results. So here we have 34%, and here we have 51%. And let's compare with the previous. Well, the second step is better, and the first step is not so good. So let's wait a little bit more. Well, again, it's looked like what we guessed, a very good seed for common model for our baseline. And that's why we get very good results even at this stage. But, well, as we can see, the baseline model achieves about 70% of accuracy only at the 8th epoch, and well, task-adapted model achieved it well at the 6th epoch, so it's also great. And well, let's recall what we adapt our model only for the 5 epochs. So if we will adapt it, for example, for a full training loop for all 100 epochs, we will get much better results. Well, but even for now, we get some not so bad results, especially compared with results that were presented in paper. So in paper, we achieved about 63% of the baseline and about, well, I suppose about, well, 67% with the top. So we achieved about 70% with the top, so it's also great. Well, it's not as well here. Yes, we achieved about 70% in F1 score. And for now, let's move to the third part, notice domain adaptive pre-training. And now we will look, well, at this setting. So we will run our model fine-tuning after the domain adaptive pre-training. So again, we have a better approach which combines domain adaptive pre-training and task adaptive pre-training and fine-tuning, but it's quite computationally expensive. So let's look at domain adaptive pre-training. One more time, we will not perform this by ourselves. So we simply load pre-training checkpoint. This is a checkpoint from the aforementioned paper, where the authors pre-trained the same base Roberta on computer science domain. So we simply load this pre-trained model. Well, this is already domain adapted model, and again run our classification pipeline on this model. So again, we'll use the same hyperparameters and everything else also the same. And run our training. Well, in this case, we expect that this model will show much better performance than a baseline model. Well, because we employ some domain adaptation for this model. And yes, as we can see, to start, we will have a higher F1 score. Well, again, which is great. So let's wait a little bit more. And again, as we can see already now, we have well, much better training dynamics what we will have, what we had for baseline model. Well, for now, we trained our model for 5 epochs, and well, we have about 75% of F1 score. Let's compare with the table. Well, it's almost similar, and let's compare to a baseline. And for the baseline, we also achieved 75%, but only at the 10 epoch. So, well, our model converges much more faster again. And overall, I suppose that we even get better results, maybe. Well, and then let's wait a little bit more. Well, here we can see what our model is start to overfitting, because we have decrease in training loss, but we have some increase in validation loss. But still, we get some good results, and finally outperform the baseline model. Well, which is great again. And well, let's wait for a final epoch. And it's done. So, well, as one can see, we finally achieved better results when we have on the baseline model. And again, if we will properly fine-tune our hyperparameters for training, we will more likely obtain even better results. And well, there is a vast space for additional improvements. For example, well, some optional task, one can combine domain adaptive pre-training and task adaptive pre-training, as it was made in a mentioned paper. So firstly, run pre-training for example, for Roberta on domain dataset. After that, run pre-training on the task dataset, and finally run some training, well, some supervised training on downstream task. In our case, it's text classification. And well, again, with this more complicated procedure, one will get much higher scores. So as we can see, the best results are achieved with combining domain adaptive pre-training and task adaptive pre-training. Well, again, there is a lot of interesting improvements for these methods. For example, in some cases, we don't have some domain dataset, or we don't have some big enough task datasets. For example, for some tasks, we could have only about 100 or 200 examples, which is not enough for running task adaptive pre-training in most cases. But for example, we can extract some additional task unsupervised data from the common used big data sets. For example, we can use the training data set for Alberta, and with for example, with the help of clusterization, extract similar instances or what are similar to instances in test dataset. So, for example, we have 100 example in our task. We calculate embeddings for these examples, for example, with Roberta model, and perform some clustering on some beacon labeled dataset. And after that, we can extract the most similar example and create additional unlabeled dataset, what we can use for task adaptation, or maybe even for domain adaptation, if we have enough data, for example. Well, so once again, there's plenty of our improvements, what one can make in this area. And well, it's quite a useful technique, what is widely used in some specific domains, especially in biomedical domain, computer science domain, and so on and so on. So again, the base rule for these methods is, well, just simply look at your data, and if your data, well, significantly differs from commonly used data, from, for example, news or articles, well, in which case you more likely want to perform some domain adaptation. Well, I suppose what this is all for today. As some optional task, again, you can perform joint domain adaptation with task adaptation, or for example, read this paper. So it's not so big, but it's quite useful because it's, well, one of simplest method of domain adaptation on one hand, and on the other hand, it's very simple, and it's gives a significant increase in performance of a model in most cases. So you can look at this paper one more time, get some insights from it, well, maybe try to somehow improve it, and so on. Well, and that's all for today. So thank you for your attention. Well, if you have any questions, you can ask them.
No questions, I guess.
Well, so again, thank you for attention, and well, goodbye.
Thank you. Bye.